All right, so in this chapter, we're going to very briefly go over chapter 31 on electromagnetic oscillations. So the first thing we'll talk about is an alternating current. Um, an alternating source is any device that produces a sinusoidally varying voltage or a current. Now compare that with the types of batteries that we've been talking about so far in the course. All of our batteries provide a fixed voltage. So you have a 6-volt battery or a 24-volt battery. And also the current that it provides is fixed, unless you've put a capacitor in the circuit or something like that. But if you just have the battery and the resistors, then you have a fixed current. But now we are talking about a voltage source which is fluctuating in time, right? And alternating source is a device which produces a fluctuating voltage, a varying voltage, and therefore a varying current, and it has to be sinusoidally varying. So that means the voltage would be a function of this type. So it would be some maximum voltage multiplied by sine or cosine uh, omega t plus phi, where omega and phi are constants. Okay, so that's an example of a sinusoidal voltage. How would you create a sinusoidal voltage? We had already seen an example of this in chapter 29. So this picture on the top right of the slide might look familiar. So you have a magnetic field, a constant magnetic field, and you're rotating a loop in that constant magnetic field. So if you apply the flux rule, as we have done in chapter 29, you will find that the EMF produced, the induced EMF is sinusoidal, and it has this particular form. The induced EMF is some maximum EMF maximum value of the EMF multiplied by sine of omega t plus phi. So it just oscillates sinusoidally, and this maximum EMF turns out to be magnetic field area of the loop times the number of turns of wire times omega, the angular velocity at which the loop is being rotated. This this was actually a problem that we discussed in chapter 29, and in my video on chapter 29, I fully worked this out. Okay. The next thing that we're going to talk about is, so this kind of uh, source is called an AC source. What is the advantage of an AC source? Well, it turns out that large electrical generators are much better suited to generating AC rather than DC. Because going back to this example, you can see that you can produce an AC if you rotate a loop through a magnetic field, right? Think about how a hydroelectric plant produces current, or a coal plant produces current. In a hydroelectric plant, what happens is that you have a cliff and you have water falling off this cliff in a waterfall. And to harness the kinetic energy of the falling water, what you do is you stick a um, turbine somewhere over here, and the paddles of the turbine turn as a result of the falling water. And so the kinetic energy of the water is converted to rotational kinetic energy of the paddle, right? So you have a rotational kinetic energy of the turbine. So you have a rotating turbine. So you can see that if you connect this to a loop and have that loop in a magnetic field, then you would generate AC. Uh, a coal plant does exactly the same thing. Instead of falling water, you've got rising steam, coal plant. Okay, so large electrical generators tend to rotate turbines, and so when something is rotating, it's easy to generate alternating current from it, right? Another tremendous advantage of AC is that it's very easy to step up or step down the voltage of an AC source using a transformer. A little later in this chapter, we will see how to do that and why that is useful. And the third thing is that AC is more readily adaptable to rotating machinery such as generators and motors. Okay. However, DC is also extremely important. So DC is what we've been studying so far in this course. DC is extremely important. Almost all modern electronic devices, such as computers, phones, basically anything that uses a power adapter or a USB cable, uh, runs on DC. So DC and AC are both equally important. Okay. Okay, so let's talk about the average power in an AC circuit. Now, in DC, you remember that the formula for power was I squared times R. Um, in an AC circuit, where the resistance is R, what is the power going to be? There is no fixed value for I because I is fluctuating. So you have to obviously find some kind of an average power. And for that, you have to use some kind of an average current. Right? So what is a good average value to use for the current? Let's think about that. So the current is a sinusoidal function. I is equal to some I max. I should probably just use little I. Little I is I max. Capital I is the maximum value of I. Sine omega t plus phi. Now, if you make a graph of this function, it's going to look like this, the standard sine graph. What is the average value of this over a complete period? So a period would be something like this. So what is the average value of a sinusoidal function over one complete period? As you remember from elementary calculus from high school, the average would just be 0. Now, how do you find the average of a function? So if you have some function of time f of t, in general, the average of f of t is going to be the integral of f of t integrated from over the period of time that you're interested in, t1 to t2. And then you want to divide that by that period of that range of the variables. So t2 minus t1. And this is just the definition of the average of a function, right? All right, so if you want to find the average of this current, then you would have to integrate the sine over a complete period. And you know that the integral of sine over a complete period would be this area, which is clearly 0. The area above the x-axis is positive, the area underneath the x-axis is negative, as you know, so the total area would be 0. So this naive averaging would not be useful in our case. So we need a different type of average, and that different average is called the RMS average. So what is the RMS average? So to find the RMS average, what you do is you first square the function, right? And then you find the average of the square. Now, I used this little bar to indicate average, but there is also another way of indicating the average, which is to put angle brackets around it. So we are just going to stick with this one. So for the first step in finding the average is to square the function, find the average of the square of the function. The average of the square of the function is not going to be 0 because, you know, if you square the function, it won't have any negative parts. Everything will be positive. So it would be entirely in the positive region of the. It would all be positive, like you won't have any negative quantity. And so the average of that f squared is not going to be 0. And then you just take a square root of this. So there are 3 steps involved. First is squaring the function, then taking its average using the same formula that we have over here, and then taking a square root of what that is. Now, suppose you carry through with this procedure over here. So you first square the function, so you find I square. So that's going to be capital I square sine square omega t plus phi. Then you integrate this from 0 to 1 period, which is omega divided by, it's 2 pi divided by omega. That is the period of this function. And then you just divide by 2 pi divided by omega. Right? So if you do this, what you're going to find, and you can just easily evaluate, you know how to take the integral of sine square by using the double angle formulas and all that. So I'll let you just work out the details yourself. It's just a couple of lines of algebra. Or you can just use Wolfram alpha to do this integral. You will find that it is equal to capital I divided by square root of 2. So that tells you that IRMS is equal to the maximum value of the current divided by the square root of 2. So you can just verify this yourself. Just to make sure you're convinced about that. And so that is the definition of that is what RMS is. And for a sinusoidal function, the RMS value of the function is the maximum value of the function divided by the square root of 2. So in the next slide, I have a plug and chug example based on that. If you're told that so when you plug something into the wall, we always say that it's 120 volts, but if it's, you now know that it's an AC, so what is the 120 volts? Like it's fluctuating all the time, so what do you mean that it's 120 volts? Well, the answer is that it's 120 volts is actually the RMS value of the voltage that the mains is providing. So the mains is providing a sinusoidal voltage, the RMS value of which is 120 volts. So this question is just asking you, what is the peak value of the AC going to be? And so you can just easily answer it from the fact that VRMS is going to be V maximum divided by square root of 2. So you can easily find what the peak value is going to be. I think it's 170 volts. So the voltage that your mains line is providing is sinusoidal, and it oscillates between plus 170 volts and minus 170 volts, and its RMS value is 120 volts. All right. Okay, I have another problem here which is worked out on the slide. You can just do this yourself. All right, so the next thing that we are going to talk about is a transformer. So what is a transformer? So here is a schematic diagram of a transformer. So it basically consists of two solenoids. One of them, which is called the primary, is connected to an AC source, and this circle with a little wiggly line underneath it is called is the circuit symbol for AC. Okay, so this solenoid is called the primary, and then you have a piece of metal which goes like this, and you can see that in this diagram nicely. So you have this piece of metal going like this, and then there is another solenoid wrapped over here. What is the purpose of this piece of metal? It just guides the magnetic field lines. So I'll just draw a few magnetic field lines here. It just guides the magnetic field lines and makes sure that they pass through the secondary solenoid. Without the piece of metal, some of the magnetic field lines would not pass through the secondary solenoid. So this metal, which is also called the core, makes sure that most of the magnetic field lines of the primary solenoid also pass through the secondary solenoid. Okay? In an ideal solenoid, both these, in an ideal transformer, both these solenoids see exactly the same magnetic field lines. All of them pass through both the solenoids. Okay, so this is basically what a solenoid is, and the ends of the secondary transformer, secondary coil are connected that represents the output. So there you connect whatever you want to provide a voltage to. Okay, the number of turns on the primary, let's call that NP, and the number of turns on the secondary, let's call that NS. And so this is a transformer, right? All right, and a much nicer diagram is over here. I mean, these are both uh, diagrams of transformers. Okay, so what's the advantage of a transformer? So to see that, let's just quickly calculate what the uh, voltage is going to be in the primary and the secondary. So let me just quickly draw the transformer again. And I'm not going to draw the core. So here you've got an AC source, and here you've got the secondary coil. The number of turns in the primary is NP. The number of turns in the secondary solenoid is NS. Okay, so we want to find out the EMF induced in the primary. So that is going to be, according to the flux rule, the magnitude of the EMF induced, and I'll just use V for EMF instead of E. So the EMF, or the voltage induced in the primary, Vp, is going to be Np d phi b dt from the flux rule. And I'm just talking about the magnitude. I don't care about the direction. So I'm not using the minus sign. And what about the voltage induced in the secondary? Vs is equal to Ns d phi b dt. Now let's think about this d phi b dt for a moment. We are talking about an ideal solenoid, which means all ideal transformer, which means all the magnetic field lines that are passing through the primary are also passing through the secondary. So they see exactly the same magnetic field, and we'll just assume that the area of each turn is the same. So remember, flux is equal to magnetic field multiplied by area multiplied by cosine theta. So you can see the flux is going to be the same for each turn in the primary, and also for each turn in the secondary. And so d phi b dt will also be the same, right? Because they're seeing the same magnetic field lines. So d phi b dt is going to be the same for both of them. So let's compare the magnitudes of the induced EMFs. So Vp divided by Vs is equal to Np divided by Ns. And this is one of the transformer equations. And I have that right here. Or in other words, you can write Vs is equal to Ns divided by Np times Vp. Okay. Now, there is another equation that you can derive very easily, which stems from the fact that the power delivered from conservation of energy, the power delivered on the primary side has to equal the power on the secondary side, because power is energy per unit time, right? So by conservation of energy, the energy that you see on the energy that's produced at that's delivered to the one coil has to equal the energy that's delivered to the other coil, right? So P times I has to be constant. So I mean V times I, P has to be constant, which means V times I has to be constant. So that means Vp Ip is equal to Vs Is. And that tells us that the currents have an inverse ratio. So Ip divided by Is is equal to Vs divided by Vp, and that's equal to Ns divided by Np. So the voltages are directly proportional to the number of turns of each solenoid, and the currents are inversely proportional to the number of turns of each solenoid, right? So this is tremendously useful. Why is this useful? Suppose I have an AC source over here. Let's say that um, this is a 6-volt AC source. However, I have an appliance that needs 60 volts, right? I could use the 6-volt AC source to produce 60 volts, to provide 60 volts. How would I do that? I would do that by just adjusting the number of turns in the primary and the secondary. So if I want to make 60 volts show up over here, what is the ratio of turns in the primary and the secondary? The answer is going to be the secondary should have 10 times as many turns as the primary, because remember that Vs divided by Vp is equal to Ns divided by Np. So if Vs is 10 times more than Vp, then Ns has to be 10 times more than Np. So as an example, if I've got 10 turns on the primary side, how many turns do I need on the secondary side? The answer is 100. So 10 times more turns on the secondary sides means 10 times more voltage. Okay. So this particular arrangement is called a step-up transformer. You can also do the opposite. Suppose you have a high voltage source, but your appliance needs a smaller voltage than what's available directly from the source. So in that case, you would just make sure that there are fewer turns in the secondary than in the primary. So more turns over here, fewer turns over here. This would be a step-down transformer. So this is going to step the input voltage down to whatever you need it to be for your appliance. So you can see that it's extremely easy to adjust the output voltage of the transformer by simply manipulating the number of turns. Okay. All right. So why is this useful? There is one tremendously useful application of this, which is in transmitting electricity. So let's talk about how transformers are useful in transmitting electricity. Suppose you have a power station over here. Power station is basically just an AC source. And you want to send, okay, let's just not assume that it's an AC source. It's some kind of, let's say it's a DC source, right? So the power station is just one gigantic battery. And you want to send electricity to a household which is very far away. Many miles away, and you want to do it through DC. So you have this wire through which is these overhead power lines, which eventually get to the house. And when the people in the house make a connection, then you have a complete circuit, and you're sending power to this household. Now, what is the problem with this? The problem is the following. Even if you're using copper wires or some wire with a low resistivity, you know that resistance is equal to rho L divided by A. So if the L is extremely large, like if you're sending this electricity, if these power lines are hundreds of miles long, then the resistance can be very large, because even though rho is small, L is very large, so the resistance can be huge. And so these power lines actually become very large resistors. So what's happening here is that a lot of power is dissipated as heat in these power lines, right? And so there is not much power left for the household. So that is the big problem. Most of your energy is being wasted as heat along the power lines. And the power dissipated as heat is I squared times R. So how can we solve this problem? One way of solving this problem is if we could somehow transmit the power with a low current, right? That would solve the problem, because in that case I square R would be small, right? So that is not possible to do, or very difficult to do with a DC, but it's extremely easy to do with AC. So what you can do is you can just have your source like this, AC source like this, and then just include a transformer. So what you want to do is you want to step up the voltage tremendously to 100,000 volts or something like that, right? So you want to tremendously step up the voltage. So here you use a step up transformer and you tremendously step up the voltage. And the result of that, since voltage times current is constant, so if you step up the voltage tremendously, the current goes down, right? So you have a low current output in the secondary, right? And so now you can transmit the current through overhead power lines, and there will be very much reduced joule heating or dissipative heating in the power lines, because the current is very small. Remember, the formula for uh, power is I square R, and so there will be a lot of power left when this gets to the household. Okay, so that is the advantage. Now, you don't want the household, you don't want people when they're plugging into the wall, you don't want them to receive 100,000 volts. So the 100,000 volts is used only when the power is being transmitted. Uh, Before the power is actually goes to a household, it is stepped down using a series of transformers again. And so for example, like while the power lines are in a place like the cornfields of Iowa or something, like there's nothing in sight for miles and miles, there they might be 100,000 volts. But once they get into a city, there they might be stepped down to 250,000 to 25,000 volts, and in a subdivision they might be again stepped down to 5,000 volts. By the time it gets to your house, it might have been stepped down a couple more times, down to 120 volts, right? So it's stepped down in a series of steps until it comes down to 120 volts. So transformers are used both for stepping up the voltage before transmitting, and stepping down the voltage at the place where the electricity will actually be used. So transformers look like this. I'm sure you've seen these drum-shaped objects on some electrical poles. So these are the transformers. Okay. Um, okay. All right, so I have a couple of plug and chug problems on step up and step down transformers, which you can look at over here. And that concludes this discussion. I'll just mention one other thing. So how do you think a power adapter works? Like your Mac has a power adapter which you plug into the wall, right? So what is that power adapter doing? Now your computer requires a voltage of about 6 volts DC, right? So your power adapter has to do two things. One is it has to step down the voltage uh, from the mains in the wall, which is 120 volt AC. It has to step that down to 6 volts, and then it has to rectify the voltage from AC to DC. So your power adapter has a rectifier. Rectifier is just converts AC into DC, right? And it also has a transformer. So these are the two things that it does. So here you've got an AC of 120 volts, and then after it comes out of your power adapter, you have a 6 volt DC, which is suitable for your computer, right? Now, let's think about one thing. The way we drew the diagram for a transformer kind of looked like this. So this was the primary solenoid and this was the secondary solenoid. The left side is the primary solenoid, the right side is the secondary solenoid. If you actually build a transformer like this, what is the problem with it? The problem is that you are connecting, let's say, the primary um, to a fluctuating AC source, right? To an AC source which is fluctuating. So there is a fluctuating magnetic field in the primary, right? You are subjecting the iron in the core to that fluctuating magnetic field. Back in chapter 29, we saw what happens when you subject a piece of metal to a fluctuating magnetic field. The result is eddy currents, right? So if you just naively design a transformer like the one showed on the PowerPoint or this design that I drew here, that is going to be a really awful, useless transformer because it will heat up very, very easily. So you are subjecting the metal both over here and over here. I mean the entire core to very rapidly fluctuating magnetic fields. So there will be eddy currents generated throughout the core, and the core will get very, very hot. And so the transformer will, this kind of transformer, if you use it for a more than 10 minutes or so, it will become a fire hazard because it will get so hot. So obviously, you have to design the transformer carefully to cut down on the eddy currents. And that's why designing a transformer is not easy. Designing a good, useful transformer is not easy, even though the principle of a transformer is very simple. So you can have a cheap transformer that will have a simple design, which will get hot pretty quickly. So suppose you are buying a power cord for your Mac because your original power cord is damaged. And suppose you go to Amazon and there is one that looks just like the Apple power cord, but it's very cheap, like under $10. Um, that is actually not a good thing to buy. Why is that? Because the reason it's so cheap is because it uses a low quality transformer, right? And a low quality transformer will do the job, but it will produce a lot of eddy currents. And so if you've ever bought one of those cheap knockoff power cords, you'll find that they just overheat tremendously. And after maybe even in a few weeks, you can't use them anymore because they get so hot. So that's the thing. So a good quality power cord will use a high quality transformer, which will cut down on the eddy currents and prevent overheating. All right, okay. So that's all that we're going to discuss in this chapter. There's a lot of fascinating stuff in this chapter, but we don't have a lot of time. So I just wanted to go over these concepts. Basically, what an AC, what an alternating current is, how it's produced, the concept of RMS, and also the concept of transformers. All right, so we'll stop here for today.